Hello there. Okay, we're going to handle the last couple of videos in Unit 2. We will not be concentrating very much on this information on the exam, or actually, we won't be concentrating on this at all on the exam, but it can be helpful for your quiz. So it's also just really cool information. So we're going to begin talking about magnetism. So we'll begin with a bar magnet. These are things that you should probably have at least a little bit of familiarity with. They're kind of like the refrigerator magnets, so to speak, just little pieces of iron that have been magnetized. Each of these has a south pole and a north pole. A lot of times we put the north pole red. We either put a red N on there or mark it red in some way, because it's just easier. So, why poles? Well, magnets are polar in the same way that charge is polar. Well, not exactly the same way, but very similarly. Um, and you remember we talked about electric fields. So, we're going to have a new thing that we're talking about with magnets called magnetic fields. Now, magnetic fields are not something that you can see, but they're something that interacts with the space around a magnet, and so we like to trace them out to get a sense of how they will interact with things around them, the magnet. So this is what the magnetic fields basically look like around one of those bar magnets that you've been playing with all of your life. Some magnets are shorter or longer or are magnetized in a different way, but they all have this basic geometry to their fields. Now, magnetic fields actually cause charges to move in funny ways. We won't go into the specifics of how the charges move, but they do cause charges to kind of wind around in circles and do all kinds of weird spirals and things like that. So that it's very important for that reason. So this video we're going to be focusing on magnetic fields and the importance of magnetic fields. And in the next video we're going to talk about how to make them. Okay, so this has some bearing on our planet. As you all know, we have a magnetic field in Earth. So let's talk a little bit about what this would look like if we took a compass, a regular compass that you use when you're camping or something like that. If we took a compass and we placed it on this field, this is what it would look like. So it will no longer necessarily point north. It would be quite coincidental if it did. It will instead point in the direction that the magnetic field is pointed in that region. So here you can see that this magnetic field line here is sort of winding around, and it comes out of the North Pole and goes back into the South Pole, and then it goes back again through the North Pole and back through the South Pole. It's almost like a circuit. So it has to go all the way in a cycle, like a racetrack. Now, if you place this compass there, it will align. The reason is that a compass is in itself a little magnet. And so you know from your own personal experience that if you take another magnet and you place it in the vicinity of this magnet, that one side of the magnet will attract to the one that we have already set. It will always attract in such a way that the south pole of one magnet will attract to the north of another magnet. So that's interesting by itself. And the reason is kind of because those lines, they really like those little racetracks that they make. And so what they're going to do is they're going to create a cycle. It's no longer going to come directly out and back in. It'll actually go into this magnet and then around, right? So the idea is, since you take this magnet and you place it like this and it automatically aligns with the field, then that is what happens on a compass. On a compass, if you place a small magnet in in a larger field, then it will align as long as you let it float or something like that. And so that's actually how we use magnets find the North Pole. And so that's why you can actually take a needle, and if you can manage to magnify the needle and put it on like a leaf on water, then it's a way that you can create your own compass in nature. So let's discuss the way that these magnetic fields play out on our planet. Now, we just discussed that if you take a compass somewhere on the planet and you let it float the way that a compass is supposed to float, it will point toward the North Pole. Now, that's very interesting and reveals a fact that may be a little bit counterintuitive. We call this pole up here the North Geographic Pole. Okay, so I'm going to write North Geo. Okay, and then we call the pole down here the South Geographic Pole, meaning that geographically speaking, North Pole I think is somewhere around right there, and the South Pole is a little bit hidden here from the angle. This is interesting. Let's take a compass, and let's go here to like West Africa somewhere. It's a convenient spot for our diagram, and place a compass there, and the direction that that compass will be pointing is going to be north, and that follows a line like so. So if you took a line all the way wrapped from the South Pole, and the shortest line that you can wrap around from the South Pole to the North Pole, then this will be pointed basically toward that North Geographic Pole. But that's really interesting because in the previous graph, what we looked at, or graphic, what we looked at was if we have a magnet, if we put a compass somewhere around our magnet, like let's say right here, and we saw that the needle pointed this way, then that means that the magnetic field would be going in the same direction as the compass. And if we illustrate that using our magnetic field of our compass, then it would look something like this. Just the same as it did in our previous drawing, right? A little rougher, but you can see what I mean by that. Now, what about the direction of these fields? This has to be going that way because that's how the compass has directed it. All of these then are going that way, right? Which means they're coming out of this pole and they're going in to this pole. Well, what does that mean about our magnet? What that means about our magnet is that we have a south magnetic pole here and a north magnetic pole here. And so basically what we're finding out, which is very interesting, is that if you took a magnet and sort of superimposed it on the very core of the Earth, the middle of the Earth. Now, there is not a giant bar magnet in the Earth, but it kind of plays like there is. So if you did that, then you would get these magnetic field lines that are very similar to what we see over there. That means that the South Geographic Pole is very close to the North Magnetic Pole, and the North Geographic Pole is very close to the South Magnetic Pole. Now that's interesting. Why? Why would they do that? Well, it turns out that when we started discovering how compasses work, we did not originally call that north pole of our magnet. We did not call it a north pole of a magnet. We called it a north seeking pole of a magnet. So our Earth has a south pole and a north pole, and the south pole is a north seeking pole, right? So that's why we get magnetic fields out of the South Pole and into the North Pole, right? Interesting. Okay, so when we look at Earth where we are, then you can see that these magnetic fields don't always come out like water would. They sometimes take little, like shortcut looking things like this. And that is also certainly true for the magnetic fields on Earth. So if you have a surface right here and you're standing on the ground, here in Arkansas, let's say, we're going to be using a compass, and our compass, let's actually go ahead and put a compass in this person's hand. Our compass might point north. Now, if this person is facing south, then the compass is going to point that way. Now, one of the things you might notice about a compass is that it has a tendency, if it's able to point north and then a little bit down, like it's pointing a little bit to the ground. That's not that's not an accident. In fact, the magnetic fields, because we're not on a perfect, like, we're not on a globe where the magnetic fields are all exactly going along the lines of the Earth. Instead, we just happen to be in a part of the globe where the magnetic field lines actually go into the Earth like this, which I think is quite interesting. If you were standing on the North Pole, like so, then you would see those magnetic fields, not the ones that shortcutted here, but you would see the ones like on the globe that we saw before that are actually coming around the top way far. Remember, this is very, very far away. So the magnetic field lines would be coming down into the North Pole. Right? If you were instead on the equator, then you would see magnetic fields going exactly to the side. So let's take a look at what we mean by that. If we take the planet to be, if we take the planet to be basically a sphere, it's very close to a sphere, and we look at the magnetic field lines that are occurring in our sphere, we'll see them doing something like this, almost as though there's a bar magnet in the middle of the planet. Okay. So essentially what we see, if we're here in our state, where our school is in Arkansas, then we're somewhere around there. Okay. And if we're right there, assuming that our pole is directly up and down here, right? Then if we're right there, you can see how the magnetic field lines are kind of piercing the planet at some kind of angle there. And if you're on the North Pole, you can see that they would be coming in exactly from above. And if you're on the equator, then you can see that those magnetic field lines would then be pointed exactly along the surface, at least roughly. Maybe not exactly, but pretty much along the surface. So, interesting. That is our introduction to magnetic fields. Remember that we can actually use magnetic fields to manipulate charge and do all kinds of cool things with it. In the next video, we're going to explore how to create magnetic fields, whether accidentally or on purpose.